Hello. In this lab, we're going to talk about GD&T and merriment. Well, the reason we're talking about GD&T and merriment is, in a lot of times when you're seeing engineering drawing of the product, you'll see a graph like this, right? It's not just the part you're drawing itself. It's actually also a lot of symbols that on the drawing. And we need to know well, what it really means and how do they use those symbols or control frames to describe the features of the product, because what you can only see here is a 2D drawing, right? How can we use a 2D drawing to describe a 3D product? And this is what we're gonna talk about in this lab. And so GD&T, the full name is geometry, dimension, and tolerances. It's a way to describe the drawing that considers the function of the part and how the part functions with its related parts. So it means how the parts actually interact with each other, or how the features interact with each other. And GD&T is also a system that it uses standardized symbols to indicate tolerances, based on the geometry features geometry. And it's a very common system of the symbols that people have been using in many countries in engineering drawings. And also there are some standards have been developed as well, for example, in ISO 9000. And so these are the typical common symbols you may see in engineering drawings, from flatness to symmetry. And we're gonna go through each one of those in this lab. The first, we need to understand some terminologies, and the one is the tolerances versus allowance. In the graph, as you can see, we have a hole. We also have a shaft. So on the left, that's a hole. Right, that's a shaft. And the allowance means we're gonna use the smaller hole and a larger shaft, right? So then we can see how much gap it is. So that is the allowance. And well, a clearance means or typically we say the max clearance means we use the largest hole minus the smallest shaft. So what is max clearance we can have? So that's the two terms, tolerance versus allowance. We need to be clear. Well, second, sometimes you may see a symbol like this, right? Is with a circle and there's an M in it, and it means maximum material condition. So basically, it describes the feature that we want wanted to have the maximum amount of materials. And it really depends on what is what is the part you're drawing. For example, if it is a hole, and if I put this M symbol here, it means we actually want a smaller hole because we want the maximum materials. Where are the materials? It's all this part except this hole, right? So only when we have the smallest hole, we can have the maximum materials. Well, on the other hand, if we are making a pin, means that if I put this maximum material condition next to it, it means we want a bigger pin, right? So this is what it means by maximum material condition. Well, understand that, then it will be easier to understand what it really means by least material condition, right? This is just the opposite. And another concept is called datum. So this, in other words, datum means that's a reference, right? What are referencing? Datum can be a plane, it can be a surface, it can be a certain line, or it can be a certain point. It really explains, or it can be axes, right? So it's a reference of the feature. And for example, in this control frame, the A means that the datum A. Here we're gonna come to this figure and see where is datum A. Datum A is really, the surface, or this one is talking about, right? This plane is talking about, this is A. And this is called datum. It can be axes or point or other features. And we just saw there's a control frame. And what is the control frame? Control frame means we are using this frame with different sections, right? The first start with what is geometric characteristic we are talking about, right? Like, for example, this symbol is a position symbol, means we're talking about the position, right? Position of something. And in the middle here, we can see this tolerance zone shape. So tolerance zone shape, and so tolerance zone, this is a diameter, right? So which means that the feature's diameter, should be within a tolerance zone of 0.25. So pay attention to here. 0.25 is not a tolerance, it's a tolerance zone from the smallest to the biggest. What is the range? Right? So that is a tolerance zone. Pay attention, this is different, is a tolerance. It's a tolerance zone. And then next to it, we use the material modifier. It's either it is material, maximum material condition, or the least material condition. So here. So in the middle, typically described this way. First, we look at what is the tolerance zone shape, right? Either it's a line, or it's a circle, or it's something else. And then we talk about this tolerance zone shape. And then what is the material modifier? Then the last part will be the datum references, right? The datum references. Here you can say, oh, well, I have 3 datum references, A, B, and C, right? Then this is the control frame. Well, how to read it? So this control frame is read as the position, right? The position, right? It's the position of the feature must be within a what? Within a 0.25 diametrical tolerance zone at maximum material condition relative to datum A, B, and C. So this is how you read this control frame. And next, let's look at what other symbols do we have. First, position symbol. Position symbol is drawn this way. And for example, if I'm looking at this, for example, this is the whole position, then actually I'm referencing 2 planes. One is this B, right? B, this is A, plane B and plane A. Then I can use these 2 to define a certain feature. And this will be the hole, right? A hole's diameter is actually within what? Within a tolerance zone of 0.03, right? 0. And what is the tolerance? This is the tolerance. So 10 is the diameter of the hole, and this is the tolerance. Plus minus 0.05 is the tolerance. And also on top of this, we also define that for the position of this hole, it has a tolerance zone of 0.03, right? So when we are making the hole, we need to consider both the tolerance and also the tolerance zone to this position, right? Relative to datum A and B, reference A and B. So this is how we read this this control frame with this position symbol. Another symbol is the angularity, and angularity is really talking about a certain plane, right? A certain plane. So for example, this one. And there's a 60-degree of angle of this plane, but when we're talking about this in the tolerance zone, it does not mean that it is 60 degrees plus minus 0.03. That's not. So this value is not talking about the angle itself, right? It's not talking about the angle itself. It's actually talking about, right? See this up and down the range, up and down the range. The plane move as a whole, right? Up and down, this wave within the 0.03 tolerance zone. This is what it's really talking about. The two parallel planes. This is within 0.03. And to a certain reference datum. Which datum? Datum A. Where is datum A? Datum A is the bottom plane, right? It's the bottom plane to this. So this is a angularity. Just pay attention to this tolerance zone. It's not talking about the angle itself. It's talking about this planes, right? Two planes apart. And another symbol would be the circularity. So circularity describes how close an object actually should be to a true circle. I describe this way. Another one is cylindricity, so which means how close it is to a cylinder, right? Parallelism is a tolerance that controls the parallelism between two surfaces or features, right? So, for example, when I'm defining this plane, right? Then in this plane, then my datum, reference datum will be datum A between this. Then when I'm looking at the parallelism, is how close it is to to be parallel of these two planes. It should be within a tolerance zone of 0.03. And we use this symbol to describe the parallelism. Another one will be the concentricity. So basically to see establish a tolerance zone for median points of a cylindrical or a spherical feature on the part, right? See this part and this part. And typically when we're describing concentricity, and we use datum as this axis, right? This axis. Profile of a surface. So describe the profile of the surface. And here are the two datums. We use this symbol to describe the profile. Perpendicularity. Similarly, we can use this symbol to define a perpendicularity with the datum A, and then for this plane, how do you define its tolerance zone here? And this is the control frame you can draw, to define the feature. And this is actually at the axis perpendicularity. This is a surface perpendicularity. Runout. So runout is basically to describe, what is a variation that is when the part is actually rotate 360 degrees, how much of the variation it is. For example, when we have this this datum A here, and then when we turn around of this whole part, and because it's not 100% of the true round, right? True circle. So there will be a little bit up and downs, and then what is this difference? What is this difference? This describes the runout. And typically you can use there's a runout device. For example, here is can be used. Here is a probe, and then when you turn part around, the probe will actually can measure the up and downs with this distance, and then you can draw the runout values. So this is we can use this arrow to describe the runout. And well, for that is only one one plane, but here we can use a total runout to actually talk about both this radial and also axial variation, right? So basically this part, right, this whole part, both the radial and also axial variation. And I use this symbol to describe total runout. Now let's compare back to this one planes. This is the one planes, right? Runout. This is total runout. And also we can use this line to describe a profile of a line. Straightness, and symmetry. I use this symbol to describe the symmetry. Typically, the symmetry would be two. We're talking about two planes, right? Two planes symmetry. Of course, we need to have a reference, and here is symmetric to what? To these two planes, right? As described, on the graph here with A. This is a flatness. Well, that's pretty much most of the common GD&T symbols you'll see in engineering drawings. And what are the measurements? Actually, we already talked about most of those, but before getting into those devices, we just need to be clear about the two concepts. One is accuracy, the other one is precision. So accuracy is to describe the degree to which a measured value agrees with the true value of the quantity of interest. So which means it is really measuring the true value, right? So that's accuracy. Well, precision means it's talking about the degree of repeatability in measurement process. For example, you can have a tool and then you measure 10 times, and those 10 times the value are significantly different. Then you can say the precision of the tool or the device is poor. But if you have a machine, if you have a device that you measure 10 times, every time you got the same values, means the precision is good, right? So it's talking about the repeatability of the measurement. And for the devices or instruments, we already have, for some of the labs, like micrometers and calipers. And this is to measure the runout. So we use a dial indicator, and there's a probe here, contact on the part. When the part rotates, then the value will actually be reflected on the dial. Then we can use the dial to find out what is the runout values. And go and no-go gauge, we already had a lab about it. And this is a protractor to measure the angles. Then next, I'll talk about the surfaces. So the surfaces are really, there are four components of the surface texture. So one is roughness. So basically, it's talking about those kind of minor up and downs. Minor up and downs here. It's called roughness. And also, if there's a bigger ones, then we call it a waveness, right? Big waveness. And these are the lays, right? These are lays. Of course, sometimes you always see craters, like this. These are the flaws of the surface. And so when we are judging or when we are, evaluating a product surface, typically we look at the surface from these perspectives, right? Roughness, waveness, lay, and also flaw. So that's pretty much everything for the lecture part of the lab. Now these are the measurement devices, and the last one is for different manufacturing processes, the surface roughness, or the tolerances of the manufacturing process is actually different. For example, machining process typically have a better tolerance, right? And but process like injection molding or casting, typically they have a little bit poor tolerances. So that's something you probably want to have an idea about, right? What different processes cause what kind of surfaces. All right, so that's pretty much everything about the lecture part of the GD&T. Next, I want to come back to this Fusion 360, and then see how can we draw those engineering symbols or GD&T symbols in Fusion 360. Well, first let's draw a simple part, okay? And say I want to have maybe draw a cylinder, not tri-cylinder, maybe a circle. Say maybe 2 inches, and then extrude it, right? Then extrude it. You go to the bottom here to be another maybe 2 inches, and then on top of this, I would like to draw another circle, and then make a hole. Oops. This, and then have to find the right point here. I can get into that. Top. Now here, there we go. And say I want to have a diameter of 0.7. And now I want to extrude cut, and the depth will be say 1 inch. All right. Now I got a part. Okay. And what we're gonna do is we want to generate an engineering drawing first. So how do we do that? We first come to design and see there's a little triangle, and click this. And at the end, you will see there's a drawing. We're gonna hit this from design, and you will see, this this little window pop up, and you just click OK. Of course, you can do some selections of a destination, like drawing templates or themselves. Also the sheet size. If you're okay with those, click OK, and then it will direct you to a interface, which is like this. So also automatically will come out a view, and you can drop by click the part at the place. For example, click it here, and then if you go to this box, you can actually choose which view it is, right? You can do front view, top view, right view, or some other views. Now I want to keep it as a front view, and then click OK. Now we get a front view of the part. So next I want to do is I want to create another view. Now just come here, you'll see the base view, click this. From there, the window comes back again. All right, next I want to, click this, but I don't want the front view again. I want to maybe a top view. I choose the top. You will see the top view will show up, and click OK, the top view. I maybe want to move this view a little bit. I'll move to the right. You can actually move it right or up and down, right? And then leave it here. What about if I want to create a cross-section view? So cross-section view means if I cut the part in the middle, right, or at a certain section, right, what will it look like inside? So that's the cross-section view. And here you come to this and say the section view, hit this, and then next it'll ask you to select the parent view. Then this is the view, it's a parent view. Generate this one. Then I will try to specify start point. This is start point. So it means where do you want to cut, right? It's a start point, and this is the end point. And then I hit enter. It will generate a view here. Maybe you can just drop it in the middle, then click OK. You will see this cross-section view. Means if you cut it in the middle, and this is what it looks like. Makes sense, right? All right. So next, when we have all these 3 views, of course you can generate some other views if you like. I just give you a description and introduction on how to use it. And next, let's start to put some symbols and the dimensions. I'll first start with dimensions. So you can come here, you will see the dimensions, right? See the dimension. If you click this, you can start to specify some dimensions you want to show. You don't want to create dimensions for all the lines, all your circles. That's not really necessary, as long as you use one dimension to tell. As long as the dimensions you created can help designer to make the part, then you are good. You don't want to miss dimensions, but you definitely do need to create all the dimensions. For example, I'll need this depths, right? I'll need this depths. But for now, I will start with the height, right, of the part. I'll create this, put it here. I know the height, and then I want to create the diameter, okay? Diameter, internal diameter, and inner, and then external diameter, internal diameter. All right, now we are good. From this internal and external diameter, I can tell, how long, what is the distance here, right? What is the distance here? So then I don't need to create another dimension to show that. Well, if a designer want to replicate this drawing, there's one dimension missing. That is, what is the length of this one, right? What is the depth of this hole? Then I also need the dimension for this. Maybe I'll just specify it from here. Depth of the hole. Right, put it here. Now we're good. All right, I create all the dimensions. Next, I want to start maybe create one control frame. For example, I would like to, if you go to symbols, you can see there's a feature. It's saying feature control frame. So hit this. Now you need to select an object, right? So which means which one are you I want to create this control frame for? I want to create control frame for this internal hole. Now create this. Hit enter. You will see a box pop up. It will ask you to specify first what characteristics, which means what is it position, it is or other things, or straightness, or something else, right? Concentricity. Let's say I want to specify the position of it, right? Position of the hole, and then it will ask you about first tolerance. Now let's say the tolerance, tolerance zone will be 0.03. Let's say 0.03, right? Start with, because this is a hole, so I'll put a diameter here. And also you can add a material conditioner. It's a maximum material condition or least material condition. Let's say I want to choose this maximum material condition. See, will all show up here. Then next, you can specify another tolerance, or you can start to follow that with the datums. Say I want to reference datum A, then first put it A here, and then click OK. Now this control frame is showing, right? So it's showing here. Then next we need to know which this datum A. We need to specify it on our drawing. Here you'll see the datum identifier. We click this, and then show which object. Now, if it say I want to use this as the object reference, then this is datum A. Right? Of course, you can change this to B, C, D, E, or F, something like that. Right? I'll keep it as datum A, and then hit OK. Now I have this control frame. Or if you want to edit, just right click, and then you'll be see the edit view. Let's see if we can do that. Edit view. It won't let me to let me edit. Well, it seems that it's you cannot just right click to do it. Well, if you're gonna do that, then maybe just delete it and then create another one. That will also work. Well, the last part of this drawing is to edit the information box here at the right bottom corner. And how do you edit? First, you need to select the box, right? Select the box. Now you'll see it's selected. And then right click, that will be edit properties. And now we'll see, say double click this, say 211. I'll say maybe 211, GD&T lab and title. I'll put it as 211 summer GD&T or some other titles, and also you can add your name, some other information. Once you're done, just finish properties. So this is how you create an engineering drawing with GD&Ts.